Assalamu alaikum warahmatullahi wabarakatuh. I'm Muhtaseem al Mahmud Nowroj, registration now 2024 CT1 113. Today, we are delving into one of the most fascinating data structures in computer science, the linker tree, which is a dynamic tree supporting a wide range of operations such as linking a tree, cutting a tree, and edge, having ultimately flexibility as opposed to the static trees discussed in AVL tree or red black tree. I, along with my teammates Nahdi, Wasif, Ibnul, and Tanim, will gladly walk you through one of the most impressive data structures ever crafted in the history of computer science, linker tree. To support our presentation, we have compiled all our project resources for you to explore. First, we have published a detailed demonstration video on the YouTube which covers the linker tree's working principles, complexity analysis, and step-by-step implementation. Additionally, our complete GitHub repository is public. It contains our full source code, implementation details, presentation slides, and the custom scripts used to generate our structural animations. We encourage you to access these resources to follow along and experiment with the code firsthand. In order to truly understand its value, we first have to look at the problem it solves. Traditionally, tree structures are fantastic, but they excel primarily at static querying. They undergo severe efficiency bottlenecks in fully dynamic contexts where relationships continuously morph or change. If we have a forest of trees and the graph change layout dynamically via online edge insertions or deletions, classical static layouts simply fail to respond inside acceptable time boundaries. Rebuilding the tree every time a collection changes is just too slow. This brings us to the linker tree or the LCT. Invented by Daniel Sleator and Robert Tarjan, the LCT maintains a forest of disjoint trees dynamically over these constant structural mutations. It achieves this by virtualizing paths. Rather than rigidly storing the exact shape of the tree in memory, LCTs break the tree down into paths. This allows them to support core dynamic queries, including edge insertion, removal, and path aggregates, all in a highly efficient O logN amortized time. To really appreciate this, we have to look at its historical context. Sleator and Tarzan published this in 1983. It was originally designed to optimize structural flow computations in complex networks. Specifically, it was built to improve network flow parameters for DNIC's blocking flow algorithm. Prior to 1983, dynamically splitting and merging complex subtrees was an open efficiency problem. No one knew how to do it fast enough. The linker tree represented a monumental breakthrough, establishing a cornerstone of dynamic graph theory. However, to understand a linker tree, we first must understand its prerequisite building the block, the Splay Tree. A Splay Tree is a self-balancing binary search tree, but with a twist. Instead of strictly enforcing height rules, it ensures that recently accessed elements are pulled directly to the root for rapid localized retrieval. To show you how exactly these play tree rotations work under the hood, I will now pass it over my teammate Nahdi.
Thank you very much to my dear teammate Mahmud for his eloquent discussion on the high-level overview of both the Splay Tree and the linker tree and the history of the development of this data structure. We will now move on to the underlying mechanisms and intricate implementation details of the tree. I am Hossain Mohammad Nahdi. My registration number is 202413013, and I will now walk you through the implementation details as well as the underlying ideas of a Splay Tree. So firstly, what is an Splay tree? A Splay tree is a balanced binary search tree maintaining its balance of having at most logN depth through a series of operations, similar to a AVL tree or red-black tree. Unlike red-black tree or AVL tree, however, it doesn't immediately adjust or rebalance. It maintains an overall balance which gives us an amortized depth of logN. When we say amortized, we understand it as the overall average maximum complexity, meaning that it can go far above logN or far below logN, all the way down to 1, but it will maintain an overall average if we sum up all the states of the depth. So coming up next, let me explore the structure of the tree. In this node here, each of these nodes represents a Splay tree as a regular node to be used for the linked tree. In the structure of the node, first we have CH2. CH2 represents the child pointers, meaning that CH0 represents the left child and CH1 represents the right child, 0 for left and 1 for right. Now, as we said, the Splay tree maintains an amortized depth of logN through a series of operations. The Splay tree maintains it by being a lazy data structure and doing lazy operation. So in the context of computer science, a lazy operation denotes an operation done only when it's necessary and done as a subroutine of sub-operation of another operation. In the context of Splay tree, however, that lazy operation denotes reversing or swapping the children. More of its operations are described in the next slide. Then we have isRoot, which simply checks if this node is the root of its localized Splay tree or not. So, as we discussed earlier, the struct node represents an underlying Splay tree itself, and each of these Splay tree has a root, and the function isRoot simply checks if this node is a root of its localized Splay tree. And also the node is considered a Splay tree root if it has no parent or if its parent's child pointers do not point back to it, which means the edge connecting them is a dashed or path parent edge. So what exactly is a lazy operation? As we discussed previously, in the context of computer science, a lazy operation denotes an operation done only when it's necessary and done as a subroutine or sub-operation of another operation. Lazy node is a node that stores some information about the subtree of the node. Lazy operation is an operation which is performed only when it's necessary. Afterwards, we lazily push the information to its children. So in context of the Splay tree, whether we have an update pending regarding the structure of the tree, we store them in the lazy node. For instance, here we have the lazy ref variable, which is discussed previously in the last slide, which denotes if we have an update pending of whether we want to swap the children positions or not. Whenever we work with that node, we use a helper function pushX, which is the structure demonstrated in this video, denoting that we apply all the updates regarding node X. After it does all the updates pending, it simply transfers the updates chronologically to its left and then to its right child. Then each of the child has an update regarding if we reverse the children of them or not. So what is the complexity? As we understand that every update takes only a constant time to be done, which is simply swapping, and we have an amortized logN depth, we will have an amortized logN complexity to apply pushX to the entire subtree of X, which will be denoted by a function called pushAll of X. So as we see in this demonstration video, if an update is pending, we swap the children positions of the node. So up next, we have the implementation of pushX. So if we go down to the implementation at step 1, we see that we swap the children of X, CH0 and CH1, which means left and right. Afterwards, if we have X CH0, if we have the left node in the tree, if it's present, if it's not null, then we simply pass down it to its left child, and if the right child is present, it denotes this line, then we simply pass down it to its right children. So afterwards, we simply say that none of the updates are currently available. We have pushed all the updates, so its ref is currently false. So what is pushAll? So pushAll is simply push, just it simply recursively goes all the way up to its root, the parent, and then pushes all the way down to X. So we see there is a recursive call to pushAll that goes all the way to X parent of X. So it is defined as not X is root. So if X is not the root, then go up. Then if you finally go up, then finally push and then go all the way down. Okay. So every single balanced binary search tree maintains its property through some sort of rotations. For instance, we have a single rotation of left and right in AVL tree, denoting them as L or R. For double rotation, we denoted them as things like left-left, which means LL in short, right-right, which means RR in short, and likewise we have left-right and right-left rotation. In case of a Splay Tree, we have, well, kind of similar operations. In general, there are two types of operations in Splay Tree, one involving the node itself and its parent, and the other one involving the grandparent as well. For the first kind, we have zig notation, which involves only a node and its parent. The second type of operation is classified into two types. One is zig-zig, where both the parent and the grandparent share the same orientation. The other type is zigzag, where parent and the grandparent share the opposite orientation. So what do we actually mean by orientation? For example, same orientation implies have child on same side, meaning that if the grandparent G's left child is parent P, then X must be parent P's left child. If grandparent G's right child is parent P, then X must be parent P's right child. Similarly, if they share different orientation, meaning for instance, parent P being grandparent G's left child and node X being parent P's right child, then zigzag rotation must be performed. Both of these cases are discussed in details in the upcoming slides. So next we have the zig notation. Zig rotation only happens when we have no grandparent G to rotate, so the node X must be a direct child of the variable itself. So what does it do? If we have X as a left child and a right rotation must be done and vice versa, making X a root, as illustrated in this video, we can see that X now becomes the root of the rotation. So up next, we have the zig-zag rotation. It happens whenever we have a grandparent of node X, as written in the slide. It's triggered when the node X, parent P, and grandparent G form a kind of straight line, which means left child of left child, or right child or right child. So in this context, we execute a same type of rotation twice, making X the root now. For example, as we see the illustration of this video, if we start from X, we perform a right rotation, then we perform a right rotation again, making X a root. So if we have left child, we perform right rotation, and vice versa. If we have right child, we perform left rotation. So up next, we have zigzag rotation, which is known as the double symmetric rotation. Like the previous, we perform a rotation on the alternating directions. For instance, if we have parent P as the left child of grandparent G and node X as the right child of parent P, we first perform a left rotation on node X, then a right rotation of node P. After that, X is the root of the tree, with P being its child and G being its grandchild. As illustrated of the video, we first perform a left, then a right rotation. We can see that here. So we perform the opposite rotations, and since the zigzag rotation itself is asymmetric, we perform different kinds of rotations in order to obtain its current state. So up next we have this play operation. Before that, we can look at the code of the rotation, which simply does everything. The rotation code here. So first we take P as a parent of X, then G as a parent of P. Then we check the rotation. So the rotation 0 for left child and 1 for right child, as we can see. If P ch1, which means the right child of P is X, then S is true. So the step 1 is take the opposite rotation, so on the opposite orientation. Then if that child exists, then simply make the parent of that child X's underlying child P. Okay, so in step 2 we have the child of X as P, as we can see here, and the parent of P must then become X. On step 3, we start working with the grandparent G. So if G exists, we know that this rotation is a zigzag or zigzag rotation, as the zig rotation itself never really has any kind of grandparent in it. So we do the similar kind of operations here. If G's second child or left child exists, if it exists, then we simply make it X, and if the right child exists, we simply make it right. Okay. Up next, we have the splay operation, which is the operation that actually retrieves the balance of the tree. A splay function simply makes X the root of the tree through a series of rotations, be it zig-zag, or zigzag rotation. It operates on a theory called path-halving, which means splaying has a massive advantage with shaping effect. It cuts the depth of every node along the lookup pathway roughly in half. So, as we see in this video, demonstration, we simply make the splay x, and x then becomes the root of the tree. This is simply what a splay function does. It simply makes x the root of the tree. So up next, we have the implementation of the code. So first, we push every kind of pending updates from the root all the way to x, which is why we call the function push all x. Then we simply loop. So how do we loop? So while x is not its root, which means while we don't have a root node, we can simply display the operation, okay? So we first take the parent p, and then we classify it into three separate rotation types. So the case one is 6-step. So if p is root, then we do not have any kind of grandparent whatsoever. So we simply call rotate x, which is simply the 6-step. So then we determine the alignment of the relative to the grandparent. So what does these two variables do? P is left. So P is left simply refers to the question if G's child P is its left child. Similarly, if X is left denotes if P's left child is X, right? So if we have both of them collinear, if we have both of them true, or if we have both of them equal, because it can be something like 0, false, which means P is right, and it can be something like false, which means X is right. So either we can have P is left and X is left, or P is right or and X is right. So if something like that happens, they're collinear, and then we proceed to the zigzag step. And as we discussed earlier, the P must be rotated first, then the rotation of X must occur. And if it's not the case, then we move on to the zigzag step. So zigzag step simply rotates X, then rotates X again. So we simply retrieve its original structure. Okay, so up next we have more Splay Tree operations. These are operations that Splay Tree supports, like insertion, deletion, find tree, most fundamental operations of a simple binary search tree or a balanced binary search tree. But they are not really elaborated because they are not irrelevant in context of implementing a linked tree. So insertion, what does insertion do? It simply inserts the element into the tree, and dealer simply deletes the element of value v from the tree, and find simply finds the value in the tree. So whatever we have, we need to show that. Okay, so thank you for letting me explain the underlying processes of Splay Tree. We now move on to the actual implementation of the linked tree, which will be done by my teammate Wasif in the next section. So thank you very much.
Thanks, Nahdi, for that solid explanation of Splay Trees. Assalamu alaikum. I am Wasif Siddique, and I will be continuing our presentation by diving into linked trees. Okay, so linked tree. Uh, uh, Now that we understand the internal mechanics of individual Splay trees, let's zoom out and look at the architecture of the linked tree as a whole. To understand and the linked tree, you have to realize we are actually maintaining two overlapping structural representations at the same time. The first is a represented tree. This is the actual user-facing logical tree or forest structure we need to maintain. It is cleanly decomposed into disjoint sets of what we call preferred paths, which are based on the most recently accessed node pathways. Connections here are designed as either solid edges, or which are preferred parent-child paths, or dashed edges, which act as path-parent linkages to other branches. The second structure is the auxiliary splay trees. Each isolated preferred path from our represented tree is mapped to its own independent auxiliary splay tree. The golden rule of an auxiliary tree is that its nodes are keyed strictly by their relative depths inside the represented tree. This means the left subtree always contains nodes that are shallower or closer to the root, while the right subtree contains nodes that are deeper down the path. The core operation we have is axis of V. Everything we do in a linked tree revolves around one foundational core operation, which is axis of V, also known as the path reconstructor. This is the single most important subroutine in a linked tree. Every other operation relies directly on it. The goal of axis of V is to restructure the forest so that a single preferred path of solid edges connects the root of the represented tree directly toward target node V. Step 1, we splay V to the root of its current auxiliary tree. Step 2, we sever its right child, making that edge dashed. We do this because V needs to be deepest node on our new path. Step 3, we splay the parent and hook V up as its right child. Step 4, we repeat this up to the absolute root. As the animation on the slide demonstrates, this dynamically shuffles solid and dashed edges to build an unbroken highway straight to V. The implementation, let's look at how this is implemented in code. XSV isolates and constructs a continuous preferred path represented as a solid splay tree stretching from the absolute forest root down to the target node X. In step 1, we start at node X and ascend the tree by climbing through those dashed path parent pointers. In step 2, for each ancestor Y we reach, we execute splay of Y to isolate it at the top of its local auxiliary tree. In step 3, we sever Y's old preferred right child, turning that solid edge dashed, and hook up our previously tracked subtree, stored in a variable called last, as its new solid right child. In step 4, we update our tracker so last is equal to y and continue upward until the true root is processed. Finally, step 5 is to perform a final splay of x to ensure our target node sits cleanly at the root of this newly consolidated path. With access built, we can identify forest component roots using find root of V. The goal is to find the absolute structural root of the represented tree containing node V, which is crucial for verifying components connectivity. Step 1. We call access to V. Because of how access works, this immediately puts V and the root in the exact same splay tree. Step 2. We traverse all the way down the left children spine of the auxiliary tree. Because nodes are keyed by depth, the true root must have the absolute minimum depth. This will always be the leftmost node. Step 3. Display the found root to maintain operational balance. You can see this lateral traversal happening in the looping video. Okay. In the implementation, serves as the backing engine for connectivity validations. After running access of X in step 1 to bring X and its ancestors into a single solid capsule, step 2 is a while loop that walks down to the leftmost child, stage 0 of the splay tree. Notice that as we walk, we execute push of X to clear any pending lazy tags, ensuring our pointers are accurate. Leftmost node is the true node. In step 3, we execute splay of X on the discovered root node to rebalance the tree and preserve our amortized order of logN time complexity bound. This makes user queries incredibly fast. A connected u, v function simply checks whether find root of u is equal to find root of v. But if we want to reroute the represented tree, we use make root of v. The goal is to force node v to become the absolute conceptual root of its represented tree. This is crucial for establishing arbitrary edges. Step 1. Call access of v. Now v is at the deepest point of its preferred path. Step 2. Splay v to the top of its auxiliary tree. Now all other nodes are shallower and sit strictly in its left child branch. Step 3. We swap the left and right child pointers of the auxiliary tree using a lazy flip bit. As the video shows, this completely reverses the depth orders of the tree. Looking at the code, making root seamlessly changes the structural hierarchy. After calling access of X to expose the preferred path, node X is the deepest node. In step 2, we apply a lazy reversal tag to X by literally flipping its bit with an XOR operation. In step 3, this tag conceptually flags the path to invert its sequence, turning left descendants into right descendants. When this lazy tag is eventually pushed, X seamlessly transforms from the deepest node into the shallowest node, becoming the true root. Now we can merge components using link of u, v. The goal of this dynamic component merger is to merge two separate forest subtrees by instantiating an edge between node u and node v. Step 1. Convert u into the root of its containing tree using make root of u. Step 2. Call access of v to ensure a clean path layout in the target tree. Step 3. Connect the parent of u's splay tree to point directly to v, forging a new dashed edge. You can see the components snapping together in the background video. The code for link establishes this brand new dynamic edge safely. Step 1. Invokes make root of u to isolate node u as the absolute structural root. Step 2 is a vital safety check. We run get root of v to confirm that even we do not already reside within the same component, which prevents us from accidentally creating a cycle. If they are separate, set tree links them by setting use parent pointer to V, creating that new dashed path parent connection. Finally, we have our dynamic component splitter, cart of U, V. The goal is to sever the existing structural connection between node U and node V, splitting the tree into separate subtrees. Step 1, reroute the tree using make root of U. Step 2, call access of V and splay V to isolate the target path. Step 3, break the connection completely by setting V's left child and use parent pointer to null. The video loop illustrates how cleanly the components break apart. To finish our look at operations, the cart code destroys an existing link. We run make use of U in step 1 and execute V in step 2. This pulls V up to the top of the Splay tree. Step 3 is critical. We verify that a directory as exory exists. We do this by checking if U is the immediate left child of V and that U has no right children. If it is a valid edge, step 4 permanently severs the physical pointers by setting V or C is 0 and U the parent of U to a null pointer. Now that we know exactly how the linked tree restructures itself in memory, I will hand over this to my teammate Ibnul, and he will explain the time complexity analysis of linked tree.
Assalamu alaikum. I'm Shaikh Ibnul Islam, registration number 2024331028. First of all, thanks to Wasif for explaining the core operations of the linked trees. Now I'll discuss the complexity analysis and briefly go over the implementation side. The complexity proof we discussed today mainly comes from the famous paper published by Tarjan and Daniel Sleator, who introduced Splay trees and later the linked trees. Since linked trees internally use Splay trees, we first need to understand why Splay trees themselves are efficient. The main theorem used here is called the access lemma. Instead of analyzing the cost of a single operation only, we use amortized analysis. Amortized analysis means that even if some individual operations are expensive, the average cost over a sequence of operations remains small. The method used here is the potential method. We define Ci as actual cost of operation I, phi I as the potential after operation I, and AI is the amortized cost. Then the amortized cost equals the actual cost plus the change in the potential. You can think of potential function as stored balancing energy inside the tree. When the tree becomes unbalanced, the potential increases. Later operations can use this stored potential to pay for expensive restructurings. To analyze the Splay tree, we define two metrics for every node x. S of x as the total weight on number of nodes inside the subtree rooted at x. R of x equal to log S of x as the rank of the node. The global potential phi is simply the summation of R of x over all nodes in the system. Using these definitions, Sleator and Tarjan prove the access lemma. The amortized cost of splaying node x is bounded by big O of 1 plus R of t minus R of x, where t is the root of the tree before the splay operations begins. Now let's analyze the individual splay cases, starting with the zig step. This case occurs when the parent of the node x is already the root of the tree. Because of this, only one single rotation is needed. The actual cost is C equal to 1. After the rotation, the rank of x increases while its parent's rank slightly decreases. By applying our potential method formulas, we can show that the final amortized cost remains strictly bounded by a clean logarithmic expression. The second case is the zig-zag step. This happens when both x and its parent are on the same side, meaning they're either both left child or both right child. Here we must perform two consecutive rotations in the exact same direction, giving us an actual cost of C equal to 2. The proof relies heavily on rank inequalities. One crucial inequality used here is that 2r prime of x minus r 2r prime of x minus r of x minus r prime of g greater than equal to. Using precise arguments and logarithmic properties, we prove the increase in the potential stays completely controlled. This structural step is vital because zigzag rotations are exactly what gives Splay trees their excellent self-adjusting behavior. The third case is the zigzag step. This happens when x and its parent are on opposite sides. We perform 2 rotations again, but this time in opposite directions, so the real cost c equal to 2. Interestingly, the zigzag step reduces tree imbalance even more effectively. The tree becomes much more balanced afterwards, which triggers a large decrease in global potential. The massive drop in potential helps pay for the 2 rotations. So even though the real physical cost is 2, the amortized cost still remains safely logarithmic. When we sum all these individual Splay steps together across an operation, something beautiful happens. Most intermediate rank terms cancel each other out telescopically. The summation collapses down to big of r of t minus r of x plus 1. Since the rank of the root t can be at most logN, and r of x is greater than 0, the final amortized cost simplifies to a clean big of logN. Therefore, Splay operations run in amortized logarithmic time. This is why Splay trees are called self-adjusting trees. Frequently accessed nodes automatically migrate closer to the root over time without needing explicit balance flags like AVIL or red-black trees. Now let's bridge this over to linker trees. Linker trees represent preferred paths using auxiliary Splay trees. Because paths are physically isolated inside Splay trees, our Splay tree amortized analysis extends naturally to this dynamic forest architecture. To make this extension hold mathematically, we define a virtual weight for every node W equal to 1 plus summation of S of U. Summing overall dashed children U using their represented subpresizes. The virtual rank then become RV equal to the log of W of V. For any auxiliary tree and its roots R, an identity holds big S of R equal to small s of R. This means that the auxiliary subtree size matches its represented subtree size perfectly, allowing us to seamlessly reuse our Splay tree amortized bounds. We also find that the potential function phi equal to summation of log of S big S of V for each node V, just like the Splay tree and complexity analysis. During an access V operation, we repeatedly move upward through multiple auxiliary trees, splaying nodes along the way. When we sum all these adjusted Splay bounds across k distinct auxiliary trees, the logarithmic terms telescope and cancel out once again. The total amortized access cost remains logarithmic, but we pick up an extra k factor in our initial complexity equation, which represents the number of auxiliary tree switches executed while climbing up the path. To secure our final bound, we must prove that the number of tree switches, k, is small. This uses heavily decomposition reasoning. Light dashed edges or a light dashed edge can become preferred at most big of logN times along any route path. Heavy dashed edges or activating a heavy dashed edge forces an existing heavy preferred edge to become dashed. This step strictly decreases the global potential entirely, paying for the restructuring cost. Consequently, preferred path changes are tightly bounded by the light edge limit, proving that k equal to big of logN. Combining all these components gives us a solid, robust big of logN amortized bound for the cooperation. If we look at the complexity comparison chart, you can see while classic static trees require big of n worst case time for dynamic modifications like link and cut, the linked tree process access, link, cut, and make root all in amortized big of logN times. Best of all, the overall space complexity remains perfectly linear big of n. Now let me briefly explain our C++ implementation. The codebase cleanly weaves together three core elements: Splay Tree mechanics, lazy propagation, and preferred path maintenance. Each structural node in our code stores a left and right child pointer, a parent pointer, and a reverse flag used for lazy evaluation tracking. Then our push function handles lazy propagation. When rerouting a tree structure, instead of immediately reversing an entire geometric path explicitly, we simply mark a Boolean reverse flag on the node. Later, when navigating through the node, the push function triggers. The children are swapped, and the reverse flag propagates down to the next level. This deferred execution keeps runtime extremely lightweight. The rotate function performs local pointer restructuring exactly like a standard Splay tree. We carefully update parent pointers, child pointers, and subtree metadata. Since an LCT tracks both internal auxiliary tree relationships and external represented tree pointers, updating these cross-references require immense care. The Splay function builds on this, repeatedly applying zigzag or zig-zig steps until the target node becomes the absolute root of its specific auxiliary Splay tree. This is the central driving force behind the structure's efficiency. The most critical function in the entire implementation is the access function. Access isolates and exposes the preferred path from a target node all the way up to the represented tree root. Internally, it loops upwards, splaying the current node, detaching its right child to break the old preferred path, and reconnecting the new path from below. Everything else builds on top of this function. Let's see how our operational functions utilize access. FindRoot first runs access on a node, then walks to the leftmost leaf of the auxiliary tree. That leftmost node is guaranteed to be the represented root. MakeRoot reroutes the structural tree by calling access, splaying the node to the top, and flipping the lazy reverse type. Finally, Link connects to entirely independent tree by running MakeRoot on the first node and setting its parent pointer directly to the second node. To disconnect elements, cut marks node U the root of the tree, runs access V, and serves the link by clearing the parent pointer and the left child of V, which must be U. Just like others, this operation directly inherits its clean logarithmic complexity from the underlying splay bounds. To verify our codebase, we test the implementation with real forest simulation. We initialize an array of independent tree nodes, invoke link to form the dynamic edges, and use connect to check component paths in real time. In conclusion, linked trees are incredibly powerful because they elegantly combine preferred path decomposition, splay trees, and amortized potential analysis to support fully dynamic forest mutations efficiently. While the implementation looks intimidating due to intense pointer manipulation, the underlying architecture is beautiful. Now, I would like to hand over to my teammate Tanim. He will discuss the real-world advantages, disadvantages, and engineering applications of the linked trees. Thanks.
Thanks Ibnul for walking us through the complexity analysis and implementation. I am Habibullah Tanim, registration number 2024331110. Now that we know how it works under the hood, let's look at the practical side. Why do we actually use linked trees and what are the engineering trade-offs? The first advantage is ultimate flexibility. Traditional trees are rigid, but an LCT natively supports fully dynamic forests. It handles edge insertions, which we call linking, and structural splits, which we call cutting seamlessly in real time. You never have to rebuild the graph from scratch. Second is high efficiency. As we just proved with our potential function analysis, it guarantees strict big O of logN performance limits. Even under unpredictable heavy updates, the operations stay incredibly fast. Third, it excels at path aggregations. Because paths are managed by internal splay trees, you can store metadata directly on the splay nodes. This allows you to query things like minimum or maximum edge capacities along any path almost instantly. However, this theoretical power comes with real-world engineering costs. The biggest challenge is coding complexity. Linked trees are notoriously difficult to implement correctly. Because you are constantly rearranging tree pointers, a single misplaced reference during a splay notation will completely destroy your tree structure. Next is the constant factor. That beautiful big O of logN bound hides a lot of overhead. High memory allocation, continuous pointer jumping, and lazy tech propagation mean that if your environment is mostly static, a standard segment tree or basic array will easily beat it in raw speed. Finally, it's simply not always needed. If your project only requires adding edges without ever cutting them, a distant set union or DSU model is vastly simpler, faster, and highly optimized. So, where do they actually shine? They're incredibly valuable in complex real-world engineering applications. A classic example is network optimization. LCTs are used inside advanced network routing systems to optimize network flow. Most notably, they accelerate DNIC's maximum flow algorithm. By swapping in a linked tree, you can pull DNIC's traditional runtime down from big O of V square E to a much faster big O of VE log V. They're also the literal backbone of dynamic connectivity frameworks. Think of a physical communication network where wires are constantly dropping out or coming back online. The LCT manages this chaotic environment effortlessly, giving you real-time component analysis on the fly. To wrap things up, the linked tree is an absolute masterclass in data structure design. It brilliantly bridges the gap between dynamic flexibility and algorithmic efficiency. On behalf of our team, thank you so much for your time. We will open up the floor to any questions.